Good afternoon, everybody. My name is Ajani Ausaru. I'll be presenting today on the dispersion of solids during nanoparticles assisted drug delivery. I'm a PhD student in University of the West Indies in Kingston, Jamaica, under the supervision of Dr. Nagarani Punakala. She's from India, but she teaches at University of the West Indies in Jamaica, former head of Department of Mathematics there. And this particular chapter of my thesis, I collaborated with her and Mr. Andre Small, another PhD student as well. So this is just an outline of today's talk, basically some preliminaries as to my talk. And our mathematical modeling will look at the velocity distribution. And we have two models, basically, dispersion without wall absorption and dispersion with wall absorption, after which we'll finalize, talk about some results and highlight some references. So our introduction preliminaries may entail dispersion theory and its applications, nanofluids, nanoparticles, circulatory system, blood rheology, and we will describe the models in details. So it was Taylor in 1953, Sir Taylor from Great Britain. He's a fluid dynamicist. He's the one who is called the forefather, the godfather of dispersion theory, which basically says that the dispersion theory is the principle that we have if movement or transport of a passive species in a flowing fluid under double action, two actions, that is molecular diffusion and non-uniform velocity distribution. And Taylor did some phenomenal work in this regard. You see pictorially here what's happening in terms of, we have preliminarily some homogeneous concentration profile that is disturbed by a positive velocity profile, which causes an imbalance in the concentration profile, both at the front and at the rear, creating what we call diffusion gradients. And then later on, after some time, we have a cloud of particles which are diffused or transported by molecular diffusion and more so by velocity or bulk movement. We call it vection. So Taylor's model made some assumptions, and it was only good for large times. And Harris would come on in 1960 to improve on Taylor's model using the so-called method of moments. But these models, the Taylor-Harris models, were said to be deficient in terms of time. They only spoke to large times. So it took Gill and Sankar-Subramanian in 1970 to come along and modify the Taylor-Harris model. And they developed a model called the generalized dispersion model, which I have used in this work. And this model was good for all times, right? And many other researchers have done a lot of work subsequently in this area. And dispersion theory has many applications in chemical engineering. One can think about chromatographic separation, the transport of pollutants and contaminants in the atmosphere and in our water bodies. One may think of, environmental science, and of course for us, the transport of nutrients and medicine and so on in our bloodstreams. So in the context of physiological fluid dynamics. So as you know, there are many types of nanoparticles, and a lot of them are of metallic origin, and some are carbon-based, and it is not, they're normally suspended. Nanofluids are very fine particles suspended in a base fluid, and some base fluids are water, oil, refrigerant, and ethanol, and so on. And it is a suspension of dispersed particles in a non-dissolving liquid. And we're talking about particles on the scale of 1 to 100 nanometers. Its applications are widespread in many areas, making transistor chips, refrigeration, automobiles, in agriculture, fertilizers, and so on. Of course, in cancer treatment, nanoparticles is seen today as the doctor of the future. All right, traditional medicine, if you think about like chemotherapy, it tends to damage a lot of organs that are not diseased or sick. And so with nanotechnology, we have more precise or targeted medicine, whereby in terms of what we call vectors, the medicine is transported where it is needed and it is more effective. So nanoparticles and nanocapsules and nanomedicine and nanotechnology in general is said to be the medicine and the doctor of the future. And when we talk about the circulatory system, we know that the heart is basically a pump that drives the flow of blood throughout the system. And in terms of the heart and the blood vessels, they comprise the circulatory system. And as you can see here, a lot of our arteries or vessels that make up our body are cylindrical in geometry, and so our mathematical models assume a cylindrical structure. And in terms of our blood rheology, as you know, blood is made up of white blood cells, red blood cells, platelets, and so on. And blood as a fluid is modeled as a non-Newtonian fluid. In other words, it doesn't follow the Newton law of viscosity. And as such, in terms of modeling, a Casson fluid is seen in terms of the literature as the best model that describes how blood actually flows. And so we will be modeling as a Casson fluid. In addition, in terms of the nature of blood and the hematocrit, which is the volume of red blood cells in a particular volume of blood, what we notice happening physiologically is that the red blood cells tend to, in the vessel, migrate towards the center of the tube or the vessel. And as such, what we notice is a depletion of red blood cells near the wall of the tube. And what this enables us to do is that we can model as a two-phase model. In other words, the core region will be modeling as a Casson fluid, and the near the walls or the peripheral region will be modeling as a Newtonian fluid. So we have a two-phase model, Newtonian as well as a non-Newtonian or Casson fluid in this case. So just to summarize our model, it captures drugs being transported in the blood as it flows through a microvessel. The solute is suspended with nanoparticles, so it is directed drug targeting, and the presence of yield stress captures the fact that we have a non-Newtonian situation, and we will be looking at dispersion of small and large time for low and high concentration. And the flow is subject to the pulsatile pressure gradient due to the pumping action of the heart. And so we consider an axial symmetric lamina, unsteady, fully developed pulsatile flow of a viscous, incompressible, nanoparticle infused, non-Newtonian fluid in the axial direction through a circular artery. And these are our assumptions. The artery wall is thin and sufficiently long so that we can neglect end and entry effects using a polar coordinate system, cylindrical polar coordinate system. We have a two-fluid model where the core region is a Casson fluid, capturing the non-Newtonian rheology, and we have a plasma region or a peripheral region, which is modeled as a Newtonian fluid. And the peripheral region is permeable or porous in nature. So here's a schematic diagram of the proposed model. So the peripheral region we see here in blue. The radius of the tube is A. A1 will be the radius of the core region, right, which will contain a non-Newtonian fluid. In the blue or peripheral region, we have a Newtonian fluid. And the plug region, since we have a Casson fluid, its radius is RP. And here are the governing equations of motion. These are the equations of motion, momentum equations. And because we have three distinct regions, as you would have seen here, we have our equations of motion in the respective regions. So in the core region here, we have from 0 to A1. In the core region from 0 to A1, this is this region here, we have our equation of motion. And in the peripheral region, we have equation number 2. And this term here would, is the Darcy's term, which would basically capture the fact that we have permeability, we have a porous region. And the constitutive equation, according to Casson, is given by equation 3. And for the Newtonian fluid, since we have Newtonian rheology here, we have Newton's law of viscosity captured in equation number 5. We have here a theoretically experimentally validated model that was presented by Priest and Secombe in 2005 for flow in microvessels. So mu1 would be the apparent viscosity in the core region, mu2 in the peripheral region, mu 0.45 speaks to the 45% presence of red blood cells, volume blood cells, in the so-called hematocrit, and d is the diameter of the vessel. Here, since we have nanoparticles infused, then the apparent viscosity would change when nanoparticles are added, and so Pastel and Foyboy in 2004 would have presented an adjustment to the model above, where dp is the diameter of the nanoparticles themselves, and phi is the volume fraction of the nanoparticles present, and mu n1 would be the apparent viscosity of the nanoparticle infused solute or solution. So the dimensionless equations of motions are given by equations 11 and 12, and the constitutive equation in non-dimensional form by equations 13 to 14, as well as a Newtonian form for the its constitutive equation. Pressure gradient is given by equation 16, since we have pulsatile flow, and in its non-dimensional form is given by equation 17, and we'll be using a method, perturbation method for solution, where the parameter epsilon is a perturbation parameter, and it is a Wohl-Mersley frequency parameter. And so we use equation 18, all right, to solve the Casson's constitutive equation and the equations of motion, and we arrive at our zeroth ordered solutions given by equations 19 through 23. And those are in our first order equations similarly, equations 24 through 27 with the corresponding boundary conditions. And here we have our zeroth order solutions for velocity in the respective regions as given here. This is the shear stress, first order solution for the shear stress. First order solution for the velocity in the plug region. And we just summarize our velocity, and our velocity distribution will be given for the respective regions given in equations 41 through 43, where the respective velocities are given prior in terms of their detail. And so just to summarize here, here we're considering two models. The first model, we're dealing with dispersion without wall absorption. And we'll be using Gill and Sankara-Subramanian solution to better understand the transport phenomena in microvascular flow. And of course, in this instance, we have nano dispersion. So this is the typical governing equation, the convection diffusion equation. And here we see W, which is the velocity that we have just derived for our model. And that's the velocity that we'll be using to solve the convection diffusion equation number 42, where this non-dimensional constant here is a Peckley's number that tells us whether the transport mechanism is dominated by convection or diffusion. And so the corresponding dimensionless initial and boundary conditions are given for the concentration, are given by equations 46 through 49. And here we have, remember, we have no flux at the boundary. And the solution of the convection diffusion equation according to Gill and Sankara-Subramanian is given by equation 50, which is a series expansion of the mean concentration and its derivatives. So with some mathematical manipulation, we solve the convection diffusion equation number 44, and we have equation number 54, and we have equation for the kn's, and the kn's are what we call transport coefficients, and in particular we have two in this case, the convection coefficient K1 and the dispersion coefficient K2. And we also solve for the FNs, which are concentrations, and we notice that we have a coupled system of equations. The FNs here, they depend on the KNs, just as the KNs here depend on the FNs. And so the initial and boundary conditions on the FNs are given by equations 58 through 61. And since they're coupled, we solve them simultaneously, and we arrive at expressions for K1 and K2, and for our F1s as well, and the solutions for F1 using eigenvalue expansion and separation of variables and so on. And so we can write K2 as such since the equations are coupled. And we also have found an analytic expression for the mean concentration in terms of these two coefficients, in terms of our K1 and our K2, as can be seen in equations 72 through 74. And we will look at the impact of these parameters. Beta 1 would be our slip parameter, tau y is our shear stress since we have Casson fluid involved, phi is our volume fraction of nanoparticles, and the Wohl-Mersley frequency parameter or perturbation parameter is given by epsilon there, or alpha squared. And just some results and discussion in terms of our convection coefficient K1, in terms of the impact of varying the respective parameters. K in this case would be our porosity parameter or permeability parameter. Look here, we're looking at some pictorial results for our dispersion coefficient K2. Similarly for K2 in terms of our nanoparticle diameter, our mean concentration as it varies with time, and our input slug length and so on. And we have some conclusions in that increase in the permeability parameter meant an increase in the size of the negative convection coefficient. However, it is less significant on the dispersion coefficient. The slip velocity parameter reflects a curtailment in the size of the convection dispersion coefficients. Increasing the volume fraction of the nanoparticles did significantly affect the dispersion process. And the peripheral layer thickness, that is 1 minus A1, as it increases causes a decrease in the size of the convection coefficient, and less so on the dispersion coefficient. The non-Newtonian parameter tau y, which represents the yield stress, the pressure gradient parameter E, slip parameter beta 1, the diameter of the tube dp, and so on, have shown a less significant impact on the mean concentration. And so we move on to model 2, which deals with wall absorption this time. We want to pursue this model since we know that the blood vessel wall interactions affect the nature of blood flow through microvessels and the transport of mass or heat in blood vessels due to conductive walls, and also human airways transport. So we basically want to understand nanoparticle assisted dispersion of, let's say, a drug in a two-phase model, taking into account that this time solute is being absorbed at the wall of the tissue. So the unsteady convection diffusion equation you would have seen previously, equation 44, is used to analyze the concentration of the solute. However, we would have to adjust for the physically realistic condition where now we have condition number 75, seeing that we have an absorption at the wall of the tube. So here we have the mass transfer Biot number, beta, which is the absorption parameter, since now we have absorption at the tube wall. According to Gill and Sanger-Serene, the solution to 44 is given by equation 77. Now we are starting at n equals 0. Previously it would have been n equal 1 since we had no absorption at the tube. So in this instance, we still proceeded as we did in model 1, and we have these coupled equations again, our kn's and our fn's, and the accompanying boundary conditions and initial conditions are given. And this time we also have an expression for the mean concentration, but this time in terms of three transport coefficients, K0, K1, and K2, where K0 is the absorption coefficient, K1 is the convection coefficient, and K2 is the dispersion coefficient. And just to summarize, this chapter deals with the convection diffusion in case of nanofluid flow with base fluid blood, two-layered model, Castor-Newtonian, with the peripheral layer taken as a porous region where the wall is permeable to the solid with an aim to study drug delivery in microvessels. We use the generalized dispersion model as proposed by Gill and Sanger-Serene in 1970 to solve the equation, and we would have derived our velocity distribution earlier. And so these are some pictorial results of what we obtained. Beta would be our absorption parameter. E in this picture, it represents pulsatility of flow, yield stress variation, tau y, volume fraction variation. Here, absorption parameter for, as it relates to K2 absorption, our dispersion coefficient, yield stress, how it impacts our dispersion coefficient K2. Here, the permeability parameter K, the vessel diameter, yes, D. Here, some graphics as it relates to the mean concentration, how it varies temporally, as well as how it varies with our absorption coefficient beta, how it varies with our permeability parameter K, and our peripheral layer thickness A1, or more specifically 1 minus A1. And so, in terms of some conclusion, the influence of the nanoparticles volume fraction parameter phi on the size of the convection coefficient, which is K1, is imperceptible, it's very minute. However, there's a shift in the cyclic nature of the time variation of the convection coefficient with phi, which is the volume fraction parameter. Dispersion coefficient K2 decreases with an increase in the absorption coefficient beta. An increase in the slip velocity constant beta 1 sees an increase in the size of fluctuations of the dispersion coefficient. We notice a less of a fall in the dispersion coefficients K2 size, accompanying an increase in the values of the nanoparticle volume fraction parameter phi. However, there's a shift in the phase of the time curves. In terms of the mean concentration, we notice as well that it is curtailed as the absorption coefficient increases. And the fluctuating component of the pressure gradient E, the diameter D, the nanoparticles volume fraction parameter phi, and the permeability parameter K, slip velocity parameter, and so on, have shown a noticeable change in the shift of the mean concentration distribution curves. And the diameter of the suspended nanoparticles dPVC bring no significant variation in the mean concentration profile. So just to conclude, there's some references that would have been highlighted here, and I want to thank you.